introduction. So this is joint work with Charles Grellois and Andrzej Murawski, who are both here at POPL. And it is about verification of higher order programs, and in particular about the theory of higher order recursion schemes and higher order model checking. So let's jump into it. So I will start the talk by introducing the scientific context and explain what is our contribution in this context. And then in the second part of the talk, I will try to show a bit of the tools and methods that we use to prove our results. So let's talk about automated verification of functional programs. So what can we check automatically about functional programs? Of course, we cannot check very much because halting problem is undecidable. But if you are lucky enough to have only finite ground types, or maybe if you've done some approximation that allows you to reason in a language with only finite ground type, then higher order model checking is a good framework in which you can decide properties of higher order programs. And this line of work has really a quite long history, but I think there's a lot of attention that has been brought to this subject since Lucong's result from 2006, that monadic second-order logic properties are decidable on infinite trees generated by higher-order recursion schemes. So higher-order recursion schemes, you can think of them as very idealized forms of higher-order programs where you only model the higher-order control flow but without the data flow. And they generate infinite tree, which you can use to represent different executions of your functional programs. And these monadic second-order logic properties, which on trees can be equivalently formulated by mu calculus or by alternating parity tree automata. I'm not going to introduce them formally, but you can think of them as some kind of regular infinite properties of the trees. So things like, they cover things like the program never reaches an error, or maybe the program terminates, or each time we observe A, then we know that we will observe B in a finite time. Or even things like at each branching point, the left subtree is finite. Okay. So this is what a higher order recursion scheme looks like. So it's a kind of grammar, but it's a higher order grammar where non-terminal can take parameters. So you have 4 components. So first you have some terminal symbols. So since it generates trees, the symbols can take several arguments, like B takes 2 subtrees and generates a new tree. C and D take only 1 subtree. And E is just a leaf of the tree. And this is how you're going to assemble the trees in the end. There are also some non-terminals, which can have higher types. So for some reason, I'm going to, from now on, call these kinds rather than types, because there's going to be some intersection types making a quick appearance at the end of the talk. So I will try to stick with kinds for these simple types. And then for each of the non-terminals, you have a reduction rule. So you have equality, which explain to which term these non-terminals can reduce. So you have S, which is a starting symbol, and it reduces to F applied to G. And then for each one, you have a term that can depend on the parameters. So such a recursion scheme generates an infinite tree. So to get the infinite tree, you start with the starting symbol S. You look at the corresponding rule, so here it's f of g. Then you look at the rule for f, so you unfold it, replacing the small f by g. And here you can see that the first symbol is a terminal symbol, so it's going to appear in the tree that you are starting to generate. Then you can apply the rule for g, and you get this. You can apply the rule for f, but this time with a different parameter, and so on and so forth. So here I'm going to rewrite this as that. And in the end, you get an infinite tree. And this is this infinite tree that we want to automatically check properties of. So the higher order model checking problem takes as an input a higher order recursion scheme. And it also takes a property that could come formulated as an alternating parity tree automaton, for instance. And then the output of the algorithm is it the case that the tree generated by the recursion scheme satisfies the property that you are interested in? So Lucong proved not only that this problem is decidable, but proved that the problem is actually n-EXPTIME-complete, where n is the order of the scheme. So you first define the order of the type as usual, saying that the base type, or the base kind, sorry, has order 0, and then the arrow kind, well, you take the maximum of the order of the left component plus 1 and the right component. So that's the standard notion. And then the order of the scheme is simply the maximal order of one of the non-terminals. So this is a really, really bad complexity, right? Because it means we have a tower of exponential whose height is the order of the scheme. And so it's natural to ask, is this doomed to be a purely theoretical result that doesn't have any practical applications? So in fact, there has been quite a lot of effort trying to implement this and to use it for practical purposes. And that has been pushed, first of all, by Kobayashi's group in Tokyo. They have developed a model checker for a fragment of OCaml called Mochi. And then higher order model checking has been also implemented by some other groups, for instance, in Oxford and Paris. And what these people report is that there seems to be a better efficiency than what is suggested by the theoretical complexity. So that means that it would be nice to have some tools that allow you to understand why somehow we don't run into this awful complexity and why this seems to be workable in practice. So to understand that, let's have a look to understand how you apply higher order recursion schemes to the verification of functional programs. Let's look at this figure extracted from Kobayashi's paper where he introduces this methodology in 2009. And see how you can convert a source program into a higher order recursion scheme. So here there's more than that, because in this paper he also introduces this method of you have a program and you do predicate abstraction to convert it to a program with only finite ground types. And then if you find a counterexample which is a false alarm, you can refine the abstraction and so on and so forth. So here we are not looking at that in this talk, so let's forget about it and only look at how you convert your source program into a higher order recursion scheme. So there are several steps, which are program transformations. So first of all, you convert a source program, which may be some fragment of OCaml, so call by value, into a call by name recursive program with booleans. But higher order recursion schemes don't have booleans, so you need to somehow eliminate them. So there are two operations. And if you look at this one first, they describe a way to eliminate booleans from that kind of programs, but it increases the size of the program. And so that's not very good if you're interested in efficiency. And they say, Kobayashi says in the paper that it would be nice to have a version of higher order recursion schemes that can deal explicitly with these data types to be able to avoid that. But there is another problem, which is that when you start with a call by value program and you transform it, you use a CPS translation, continuation passing style, and the continuation passing style transformation from call by value to call by name looks like this. And you see that there is a nesting of arrows on the left-hand side, and so this increases the order. And since the complexity is phrased in terms of the order, this means that these translations are not going to be tight, and you're not going to be able to have a very fine understanding of the complexity of your original verification problem by reduction to the model checking problem of higher order recursion schemes. So this prompted people in the higher order model checking community to look at specific problems that do not reduce to higher order recursion schemes model checking. So this work, for instance, starts with higher order recursion schemes and enrich them by adding a new kind, D, which is a kind for finite data type which contains k elements. And then there is a case construct which allows you to branch depending on the value. Then they prove that reachability is n-EXPTIME-complete for that. And then there's another work that provides a model checking algorithm for HORS with cases, which are a slightly more permissive way to do the same thing, to enrich recursion schemes with data types and branching. And finally, a third work going in this direction is a work by Tsukada and Kobayashi, where they prove that reachability for call by value programs of depth n is n-EXPTIME-complete. Now, depth is not the same measure that I had before. It's not the same as the order. So the depth of the ground type is 0, and the depth of the call by value arrow is the max of the depth on both sides plus 1. So it's more symmetric. Now, if you're French like me and you come from close to the linear logic community, you cannot help but think that maybe there is some linear logic going on here. Why that? Because, well, we know there is Girard's translation that decomposes the arrow in call by name as a linear arrow. So this is an arrow where you can use the argument at most once, and a bang operation which allows you to replicate a resource. Why is that relevant here? Well, because if we look at the definition of the order, you see that there's a +1 on the left-hand side. And it's natural to ask whether this +1 would correspond to this bang over there. And it's even more natural when you look at what happens in call by value, because the call by value Girard translation has the bang outside of the linear implication. And this looks very much like the definition of the def I had before with the +1 completely outside. So essentially what we have done is trying to make this intuition official and try to kind of have a refined complexity analysis on recursion schemes that uses this idea. But instead of having an explicit bang, what we do is that we use a language that has both a linear type and a non-linear type. And then we use this idea of linear continuation passing by Josh Berdin and colleagues, where what they observed is that the standard call by value CPS translation can actually be typed or kinded, I guess, in a slightly smarter way, observing that the continuation here is going to be used at most once in the translation. And so here you get rid of one of the bangs implicitly. Okay, so that's what we want to do in a nutshell. So we started by taking higher order recursion schemes and extending them with a linear row type and a product type, which is also very useful for what we do. And then we proved the following theorem. So it's a bit intimidating maybe, but model checking properties expressed by something called linear, non-linear alternating parity tree automata, yes, on linear HORS is n-EXPTIME-complete for linear HORS of linear order n. So I will explain what some of these things are. Something that I will not explain is this stuff here. The general idea being that normally properties are expressed by alternating parity tree automata, but here we have to generalize it a little bit because we need that automata interact well with the linearity information, essentially. So there is a small proviso here. We also need some additional constraints saying that the types, the kinds, have bounded linear depth. So this is a technical condition that I will not present further in the talk. Now, once we have proved this result, we can look at the three particular cases of higher order model checking algorithms that I've mentioned before. And then, whereas before these things did not have a tight encoding to higher order recursion schemes, now they do. Because here we can have the church encoding of this data type that uses only linear kinds. And that means that it has no effect with respect to complexity, so we can eliminate it. We can do the same on the right-hand side, using a slightly smarter or slightly different church encoding. And finally, we can do it for call by value as well, using this linear continuation passing idea and also the church encoding for Booleans. And the good news is that all of these encodings are tight, and so you can deduce from our theorem the following things. So MSO model checking is n-EXPTIME-complete for this and that. Also we look for call by value not just at reachability, but a resource usage problem for which you look at properties expressed by deterministic parity automata. So that's the end of the first part of the talk. Now I will try to present a few of the tools and methods we use to prove that. So first of all, this is a slight simplification of the grammar of kinds we use. So we have linear row, non-linear, and we have this product type. Then we define our complexity measure, so linear order, which is defined as the order for the non-linear row, but for the linear type constructors, it passes through them just taking the maximal. So there is no +1. So these things do not have any impact in the complexity of the algorithm, or a very minor one anyway. Now we can look at the kinding rules. So the judgment, so this is standard stuff for languages that have both linear and non-linear type constructors. So we have a non-linear context for variables that you can use several times, and we have a linear context. And then there are two rules, application abstraction for both linear connectives and non-linear connectives. And I bring your attention to the fact that for the application here, we have to split the linear context because one linear variable cannot occur both in T and U. On the other hand, for the product, when you do the tuple, then there is sharing. I mean, this is the standard rule for product in linear logic, but if you have a linear variable, you can use it in all of the tuples because you know that only one of them is actually going to be visited in execution. And this sharing is very useful for us in the translation that we do. So now on the left-hand side, I have the same recursion scheme that I started with. And using this linearity information, you can have a smarter kinding for it, where now we only use these linear type constructors. And so that means that this recursion scheme, so it's really the same thing going on, it's just the kinding is different. And this recursion scheme that had order 2 before, because these non-terminals here have order 2, now has linear order 0. So that means that linear kinds increases the expressivity without impacting the complexity. So that's really nice. And it's actually strict because the 3D generates cannot be generated without linearity by a higher order recursion scheme of order 1. Okay. And so then there's the question of how we do the model checking algorithm. So let me give you a few milestones in how high order model checking algorithm. So, okay. So first I mean, I will in this slide I will start by Lucong's result in 2006, and his methodology used game semantics. Then after he came up with this result, different people tried to reprove the same results using different tools, things closer to what they would use. So there's a paper by Haig and others using automata tools from automata theory. And then there's the Kobayashi paper that uses intersection types, so first for a restricted set of properties. And there's also work by Salvati and Valukiewicz using Krivine machines. And there will be a lot of things to say here, but instead I'm going to focus on the middle line of work. So this first work was then extended by Kobayashi and Hong to full MSO properties using intersection types. And then this was later revisited by Grellois and Méliès, using somehow trying to put on the foreground the structure coming from models of linear logic that they observed in this intersection type system. And this is thanks to this work that we could, I mean, there is some other work that I'm not going to say a lot about, but using finite model of the lambda calculus, which is really nice. But our work builds on that, and because they are so close to tools from linear logic, it was really easy to take their intersection type system and exploit this linearity. So now we have the kinds on the right-hand side, and on the left-hand side we have intersection types that refine those kinds. So the ground kind, for instance, is refined by the states of the automaton we want to verify. I mean, that expresses the property we want to verify. And then the difference between the nonlinear and the linear arrow is that for the nonlinear case, you have an intersection here. And this intersection causes a power set in the number of refinements, I mean the set of refinements, and this is where the exponential comes in the model checking algorithm. Whereas in this case, there is no intersection on the left, so there is no power set, and so there is only a minor impact on the complexity. So this intersection type system allows us to construct a parity game, which is finite, and then we can solve it in quasi-polynomial time using standard algorithms. Now the complexity analysis follows from the trying to understand what is the size of the parity game, and which essentially amounts to counting the number of intersection types that refine a particular linear kind. And this is how we prove the theorem. So conclusion, linear HORS, they allow more expressivity than standard HORS for the same asymptotic model checking complexity, so that's really nice. They allow us to unify and extend other higher-order model checking algorithms that did not have before a tight reduction to higher-order recursion schemes. And what we want to, what we really, I mean, what I would like you to take home is the fact that this is a tool that can really be important and useful to understand and to tame the complexity of higher-order model checking. So if you prove a general property of higher-order model checking, you should really not prove it for higher-order recursion schemes, but you should prove it for linear higher-order recursion schemes because it would be more general, and by translation, you can then apply it to more cases. And so then there are lots of perspectives. So here I've presented what is generally referred to as the local model checking problems, but there are generalizations like the global model checking. We would like to understand better the expressivity in terms of the infinite tree generated that we have using these linear high-order recursion schemes and how they relate to the standard kind of hierarchy of infinite trees. And finally, I guess an open-ended question is its linearity may not just be useful as a way to translate other constructs. I mean, maybe if I have a program, I know that some arguments are only used linearly, and maybe I can exploit this linearity information in the model checking algorithm using tools like that, and that could be possibly useful in practice. Maybe linearity should be inferred, or maybe in programming languages like linear Haskell, I suppose, where it's there, it could be exploited to speed up verification. So thanks for your attention.
Any questions?
Have you thought about applying this to languages like Rust, which do use linear types or affine types?
I mean, this is really where this shines is for purely functional languages, and so Rust is more of a low-level language where you talk about the memory explicitly. So I don't see a connection being there, not in any obvious way, at least.
Thank you.
Okay, thank you. So you cut out the part from the diagram you showed earlier in the slides, but I think one of the reasons why the recursion scheme model checkers work okay in practice is because of the counterexample loop. They only uses the so in the intersection types setting, it only uses the types that actually matter. Would this is there any relation to what you discovered with linearity to the fact that in practice not too many types are required?
Sorry, I'm not sure I understood. Can you repeat the question? I'm sorry. I think.
So as I understand, one of the key reasons why recursion scheme model checkers work okay in practice is because not all types are actually required. Yes. So if you think about how many types are there of order k, or there are n-EXP, many. But not all of these are required. And the Siga loop is used to discover the relevant, or likely relevant types. Okay. And you cut out that part in the earlier diagram in your slide. But, can you factor that in and combine with the linearity result and make some comment?
So I'm sorry, I don't really understand the question. So maybe we can discuss about that later. I mean, I would be interested to understand better what you're saying. Sorry about that.
Okay.
Maybe Charles wants to.
I think that with the linearity, you can even restrict a bit more the amount of intersection type you want to consider. Because in some of them, you will know that in some terms, which are the ones where there is linearity, you won't have an intersection.
Right,
So
yeah. That's what I thought. Yeah. Thank you.